Greetings and welcome to lecture number 20 on the course Introduction to Fourier Analysis. On the previous lecture, we defined the convolution between a tempered distribution lambda and a Schwartz function phi. Perhaps surprisingly, this was defined as a function on Rd rather than a tempered distribution. The value of this function at a point x in Rd was given by evaluating the distribution lambda at a certain translation and reflection of the function phi, namely tau x of tilde phi. We recall that tau x of phi at y equals phi at y minus x, whereas tilde phi at y equals phi at minus y. Combining these two definitions, tau x of tilde phi at y equals phi at x minus y. The point of this definition of convolution was that if both lambda and phi happen to be functions, then the definition would coincide with the usual definition of convolution. Now that we have defined the convolution between lambda and phi as a function, we need to know more about this function before making any further progress. In particular, we would like to know that this function defines a tempered distribution, so that we may talk about its Fourier transform. This is indeed the case as we justify in theorem 4.20. Let lambda be a tempered distribution and let phi be a Schwartz function. Then, first of all, the convolution between lambda and phi is an infinitely differentiable function, and the convolution commutes with derivatives in the usual way. Namely, if alpha is any multi-index, then the alpha derivative of the convolution equals the convolution of d alpha of lambda with phi, which further equals lambda convolved with d alpha of phi. It is worth pointing out that the second two expressions here are always well defined. They both represent convolutions of certain tempered distributions, either lambda or d alpha of lambda, with certain Schwartz functions, either phi or d alpha of phi. So they are some kind of strange functions by our previous definition. The main news about this line is that the left-hand side, which refers to the pointwise derivative of the strange function lambda convolved with phi, actually makes sense and agrees with the other two strange functions. The second part of theorem 4.20 is perhaps even more surprising. It says that the convolution between lambda and phi is a polynomially bounded function. There exists a positive constant c and a natural number n, such that the absolute value of the convolution evaluated at x in Rd is bounded from above by c times 1 plus the norm of x to the power n. If this inequality seems completely magical to you, you should remember theorem 4.8, which was our very first result concerning tempered distributions. This theorem said that the values of any tempered distribution are bounded from above by one fixed n norm for some finite natural number n. This index n is precisely the one which also appears here, in the upper bound for the convolution. To prove theorem 4.20, we need one technical lemma whose proof we will unfortunately skip in these lectures. This is lemma 4.21, which states that the difference quotients of Schwartz functions converge to derivatives, or more accurately partial derivatives, in the metric of the space of Schwartz functions. Unfortunately, this metric has been denoted by d, which is also the dimension of the ambient space Rd, but I hope that this notational clash will not cause too much confusion. To state lemma 4.21, let j be an index between 1 and d, and let ej be the jth standard basis vector in Rd, which has 0 in every other component and 1 in the jth component. Then let phi be a Schwartz function, and for every positive number r, define another Schwartz function delta r of phi as the following difference quotient. The value of delta r of phi at x equals the difference between phi at x and phi at x minus r times ej divided by r. Probably everyone knows from calculus that these difference quotients converge to the jth partial derivative of phi pointwise as r tends to 0. The content of lemma 4.21 is that this convergence also takes place in the metric space S, D. In other words, the Schwartz functions delta r of phi convert to dj of phi, namely the jth partial derivative of phi, in the metric space S, D. As I already mentioned, we will skip the proof, which requires a bit too much computation to present nicely in this format. For a reference, see Lemma 7.17 in Walter Rudin's book Functional Analysis. Perhaps surprisingly, the proof uses the Fourier transform, so it is not a brute force argument, only based on the definition of the metric D. We are then prepared to prove theorem 4.20. Let us briefly glance over the statement to remember what we are about to prove. We will start by showing that the convolution between a tempered distribution lambda and a Schwartz function phi is an infinitely differentiable function, and these three relations hold for the alpha derivatives of the convolution. The claim about polynomial boundedness will be shown at the end of the proof, and we will recall the statement at that point. The easiest part of the proof is the second equation concerning the alpha derivatives of the convolution. This is easy because both of the expressions d alpha of lambda convolved with phi and lambda convolved with d alpha of phi already make perfect sense, and the statement about their equality contains no information yet about the possible differentiability of the convolution. To prove this statement, we fix a multi-index alpha and observe that d alpha of lambda is again a tempered distribution, and d alpha of phi is again a Schwartz function. So the two convolutions we consider here are defined by our general definition, definition 4.19, of the convolution between a tempered distribution and a Schwartz function. The fact that these two convolutions agree is just a matter of some computation. Fix a vector x in Rd and start by writing out the definition of the convolution between d alpha of lambda and phi evaluated at x. This equals the distribution d alpha of lambda evaluated at the translated and reflected Schwartz function tau x of tilde phi. Next, we apply the definition of the alpha derivative of distributions. The previous expression equals minus 1 to the power order of alpha times lambda evaluated at the Schwartz function d alpha of tau x of tilde phi. In the next step, we just pull in the factor minus 1 to the power order of alpha by the linearity of the distribution lambda. Now we arrive at the least trivial step of the computation. We observe that minus 1 to the power order of alpha times d alpha of tau x of tilde phi is the same function as tau x of tilde of d alpha of phi. You are not expected to see this relation immediately in your heads, but the proof is just a computation using the chain rule in higher dimensions. I think that very few people would stay awake if I tried to calculate the details, so verifying this equation is left as a voluntary exercise. But now we are done. The distribution lambda evaluated at the Schwartz function tau x of tilde of d alpha phi equals, by our definition of convolution, the convolution between lambda and d alpha of phi evaluated at x. Since x was an arbitrary point in Rd, we have now shown that the convolution between d alpha of lambda and phi is the same function as the convolution between lambda and d alpha of phi. But we still don't know virtually anything about this function. Next, we start the key part of the proof, where we claim that the convolution between lambda and phi is an infinitely differentiable function on Rd, and the alpha derivative of the convolution coincides with the convolution between lambda and d alpha of phi. The proof of this statement proceeds by induction on the order of the multi-index alpha. The base case where the order of alpha is 0 is clear. Then alpha is the empty multi-index, and the claimed equation just means that the convolution between lambda and phi equals the convolution between lambda and phi. Let's then assume inductively that the claim has already been established for all multi-indices alpha of order up to some natural number n, at least 0. We then need to show that the claim also holds for every fixed multi-index alpha of order n plus 1. We fix such a multi-index alpha, and we decompose the derivative d alpha as the composition of the derivatives dj and d beta, where the order of the multi-index beta is 1 lower than the order of alpha, so the order of beta is n, and dj is the jth first order partial derivative, where j is some index between 1 and d. At this point, we will apply our induction hypothesis to the multi-index beta. We first write d alpha of lambda convolved with phi as dj of d beta of lambda convolved with phi. Then, since the order of beta is n, we may commute the beta derivative inside the convolution by the induction hypothesis. Namely, the previous expression equals dj of the convolution between lambda and d beta of phi. To save some space in the future, we now abbreviate d beta of phi by psi. Then psi is just some Schwartz function, and you don't need to keep in mind that it was obtained by differentiating another Schwartz function. With this new notation, what remains to be done is to show that the jth partial derivative of the convolution between lambda and psi exists and equals the convolution between lambda and dj of psi. Showing this will be based on the lemma we mentioned earlier, lemma 4.21. To apply the lemma, we let ej be the jth standard basis vector in Rd, we let r be a fixed positive constant, and we recall the shorthand notation for difference quotients, which we already introduced in lemma 4.21. Namely, we abbreviate the expression 1 over r times the difference between lambda convolved with psi at x and lambda convolved with psi at x minus r times ej as delta r of lambda convolved with psi evaluated at x. Here is a reminder of how delta r of f looked for a more general function f, and you can check that the expression above agrees with this definition with the choice f equals lambda convolved with psi. We now arrive at one of the key steps of the proof. For any fixed positive number r, the delta r operator commutes with convolution. In other words, delta r of lambda convolved with psi equals the convolution between lambda and delta r of psi. Checking this equation is only based on definitions but takes quite a few lines, and we leave the details as an exercise. We then take the right-hand side of this equation and spell out what it literally means. The convolution between lambda and delta r of psi evaluated at x equals the distribution lambda acting on the function tau x of tilde of delta r of psi for all vectors x in Rd. Here, since psi is a Schwartz function, we may apply the previous lemma, lemma 4.21, to deduce that the functions delta r of psi converge to the jth partial derivative of psi in the metric space s, d as r tends to 0. Furthermore, it is easy to check that the translation tau x for any x in Rd and the reflection tilde define continuous self-maps of the space s, d. It therefore follows immediately from the convergence of delta r of psi to dj of psi that also the modified versions tau x of tilde of delta r of psi converge in the metric d to the function tau x of tilde of dj of psi as r tends to 0. And let us emphasize that this conclusion is true for every vector x in Rd. The proof is now almost complete, we just need to collect all the ingredients. Recall that the only remaining task was to show that the jth partial derivative of the convolution between lambda and psi exists and equals the convolution between lambda and dj of psi. To accomplish this, we fix a point x in Rd, and we start by writing out the definition of the jth partial derivative of the convolution at x. This equals the limit as r tends to 0 of certain difference quotients of the function lambda convolved with psi evaluated at the point x. And we had abbreviated exactly these difference quotients by the delta r notation. Of course, this first equation only makes sense if the limit here exists, but this will follow from the next equations. In the first step, we just recall that the difference quotient operator delta r commutes with the convolution, as we observed in equation star above. Next, we spell out the definition of the convolution between lambda and delta r of psi at x, which equals lambda evaluated at the Schwartz function tau x of tilde of delta r of psi. We observed above in equation double star that the Schwartz functions tau x of tilde of delta r of psi converge to the Schwartz function tau x of tilde of dj of psi in the metric d. But lambda is a tempered distribution and hence continuous in the metric d. So the limit as r tends to 0 of the distribution lambda acting on these functions equals the value of lambda evaluated at the limit of the functions, namely tau x of tilde of dj of psi. Finally, this line here is nothing but the definition of the convolution between lambda and dj of psi evaluated at the point x. This chain of equations shows that the jth partial derivative of lambda convolved with psi exists and equals lambda convolved with dj of psi, and this is what we claimed. This completes the first part of the proof of theorem 4.20 and in particular shows that the convolution between lambda and phi is an infinitely differentiable function on Rd. In particular, as a very weak but useful corollary, the convolution is a Lebesgue measurable function on Rd. We then turn to the second part of the proof, where we claimed that the convolution is a function of polynomial growth. In other words, there exists a positive constant c and a natural number n, such that the absolute value of the convolution evaluated at x is bounded from above by c times 1 plus the norm of x to the power n for all vectors x in Rd. As we already mentioned, this proof is based on theorem 4.8, which promises that the values of the distribution lambda are bounded from above by one single n norm for a fixed natural number n. There exists a positive constant c such that the absolute value of lambda evaluated at the Schwartz function phi is bounded from above by c times the n norm of phi. This information can be easily applied to bound the convolution from above. Namely, if x is a fixed vector in Rd, then the absolute value of the convolution between lambda and phi evaluated at x equals, by the definition, the absolute value of lambda evaluated at the Schwartz function tau x of tilde phi. Further, by the inequality star mentioned above, this quantity is bounded from above by c times the n norm of the function tau x of tilde phi. Finally, we simply spell out the definition of the n norm of tau x of tilde phi, which equals the sum over all multi-indices alpha of order at most n of the L infinity norms of the functions 1 plus the norm of y to the power n times the alpha derivative of tau x of tilde phi. To proceed from here, we record two elementary facts. First, if alpha is a fixed multi-index and x and y are vectors in Rd, then the alpha derivative of tau x of tilde phi evaluated at y equals the alpha derivative of phi evaluated at x minus y. To be precise, there would also be a certain power of minus 1 appearing in this equation, but we make it vanish by placing absolute values on both sides. Second, we record an inequality which is valid for all vectors x and y in Rd and which we have already used on earlier lectures. 1 plus the norm of y to the power n is bounded from above by 1 plus the norm of x to the power n times 1 plus the norm of x minus y to the power n. Of course, if you manage to verify this inequality with the natural number n equal to 1, then the general case follows by raising both sides of the inequality to the power n. With these observations in hand, we may proceed to estimate the L-infinity norm appearing in the previous inequality. Namely, fix a vector y in Rd and a multi-index alpha of order at most n. Then, by combining both of the two elementary observations we just recorded, the absolute value of 1 plus the norm of y to the power n times the alpha derivative of tau x of tilde phi evaluated at y is bounded from above by 1 plus the norm of x to the power n times the absolute value of 1 plus the norm of x minus y to the power n times the alpha derivative of phi evaluated at x minus y. Now, the point is that the same vector x minus y appears both in the factor here and inside the argument of d alpha of phi. So this absolute value can be bounded from above by the L-infinity norm of the function 1 plus the norm of z to the power n times d alpha of phi. Finally, since the order of the multi-index alpha was at most n, this expression is bounded from above by the n norm of phi. We now have all the ingredients to complete the proof that the convolution between lambda and phi is a polynomially bounded function. Let's once more fix x in Rd and start from the absolute value of lambda convolved with phi evaluated at x. We will simply concatenate the estimates we have already established earlier. First, this expression was bounded by c times the n norm of tau x of tilde phi, whose definition we wrote out explicitly as the finite sum you can see here. Second, just above, we obtained an upper bound for each of the individual terms in this sum. The upper bound was of the form 1 plus the norm of x to the power n times the n norm of phi. Finally, we observe that there is no longer any alpha dependence in the terms which we are summing over the multi-indices alpha, so they can all be pulled out of the sum. All that remains of the sum is the cardinality of the multi-indices alpha of order at most n, which can be bounded from above by n to the power d. This is not a very sharp estimate, but it suffices for our purposes. This way, we arrive at the upper bound c times n to the power d times the n norm of phi times 1 plus the norm of x to the power n. This inequality holds for all x in Rd, and the product of the first three factors is just some finite constant which does not depend on x. We have now managed to show that the convolution between lambda and phi is a polynomially bounded function, which completes the proof of theorem 4.20. The most important corollary, at least for us, is that the convolution between a tempered distribution and a Schwartz function is again a function which defines a tempered distribution. So we may calculate its Fourier transform. This will be the topic of the next lecture. This completes lecture number 20 on the course Introduction to Fourier Analysis. Goodbye for now.